some of this already before. Okay, so we define as a galvanic cell anything that reacts spontaneously and produce some energy. I just need to get my pen.
Are you in class?
Yeah, I am. I'm just looking for my pad. I'm looking for my pad. So, so low but already. So when we have a galvanic cell, usually we have two reaction that is happening at the same time, and that two reaction is your oxidation reduction reaction. And what they do is they produce an amount of energy that we can term as cell voltage, electromotive force, or cell potential. Okay, and whenever we have here, we already discussed about the anode, the cathode. So what happened in the anode? That's where oxidation takes place. In the cathode, you have your what we call reduction. So we also know from last meeting, electron who travels from A to C, okay, A, B, C, okay, from anode going to the cathode. And the salt bridge role is to make sure that it maintains neutrality, okay, because if there's a loss of electron or gain of electron, so one will be positively charged and one will be negatively charged. So what happened, okay, the cation and the anion in the salt bridge will maintain that electron neutrality. So we also discussed about this, what we call cell diagram, wherein we put the anode on this side and the cathode on this side. And each vertical bar that we have here means a difference in physical state. So the double bar that we have here, that's what we call the salt bridge. Okay. So we have encountered the so-called reduction potential from our previous meeting. And reduction potential is just a table that shows the potential of a given reduction reaction. Now, the question is, how was this table obtained, or how was this table prepared? So what they did is they react, okay, the half reaction with a standard hydrogen electrode, which in this case is your hydrogen electrode. So you have there an HCl, which is usually converted to hydrogen gas, or it could be hydrogen gas that is converted to H plus, because you set a number here for this hydrogen electrode as 0. Now, when zinc electrode was react or combined with this one, so you end up with this cell diagram. So here you will have your anode, and here you will have your cathode. Okay, and if you're going to look at this, the one that happens in the anode is the oxidation, and that would be zinc producing zinc 2 plus and 2 electrons. Okay, now the one that happens in the cathode, that would be hydrogen plus 2 electrons producing hydrogen. So if you're going to look at the overall reaction, you just combine what is happening in the anode and the cathode. The only one that will cancel out here is your electrons. Okay, now when they combine this thing, so the reduction reaction that we have usually, okay, for a standard hydrogen electrode is this one. And the value that we have for that is equals to what? Anyone? If you recall the lecture that we have last time, the value that we have for that is 0. So what does it mean? If we reverse the reaction, we're going to have the same value. If we reverse the reaction, we're just making it into an oxidation reaction. Okay? So when zinc was combined with hydrogen, they found out that there's a cell potential that registered as 0.76. Now, we already discussed from the previous meeting how we get the cell potential, but I find it a little bit confusing compared to the one that we discussed today. Okay? Well, my students would always have a hard time doing that. So what I tell them is just to follow what we're going to do today. So the cell potential here is just whatever, okay, the cell potential in the reduction reaction. All you need to do is to identify which is the cathode and which is the anode. Okay? So in the reaction that we have here, if we're going to get the reduction potentials that we have here, so if we have the zinc 2 plus 2 electrons producing zinc, okay, usually it has a cell potential of what? Negative 0.76. Now the question is, how were they able to obtain this value? Okay, how does the reduction potential of zinc end up with 0.76 as seen in the table? So if we're going to look at what happened here, so we have what? The cell potential equals to the cathode minus the anode. Now, what is provided here in this slide? What is this 0.76 equal to? Anyone? Which one is 0.76 here? Are you there with me? Anyone? What is this 0.76 equal to? Where will I put it? Will I put it here? Will I put it here? Or will I put it here? Which number will I put this 0.76? So we'll put it in 1. Okay, so that means that's 0.76. So what else do we know? This one is the one that we're looking for. So what else do we know? We also know the E anode. Why? Because from the previous slide, we says there, the reduction potential of a hydrogen is 0.0. So here, the hydrogen is what? Reduction. So the one that we're trying to get here is the E cathode, because this one is equals to 0. What is that E cathode? That is your zinc 2 plus producing zinc. So if we're going to rearrange this one, what would be the value of your E cathode? Or the one that we could say the zinc 2 plus producing zinc. That is your E cathode. And whatever value with that would be the value in the reduction potential table. So if you're going to rearrange everything here, you will end up with what? E cathode equals to 0 minus 0.76. Is that how we end up with this thing? Or we know that will end up as negative 0.76. So the way I try to explain this to you is I'm just trying to get you on how this value was generated. Because all these values that I have there, you plug it or you combine whatever the reaction is with this reaction. So we're trying to get the cell potential of the cathode. Oh no, this is 0. I think this is not the cathode. This is the anode. My mistake. So this one is 0, and this is the one that we're looking for. So if we end up 0.76 equals to 0 minus E anode. So E anode is equals what? Can we say it like this? So you end up as negative 0.76. So what is your E anode? Okay, that's the one that you have for your sink. So let's try another one. This time, the copper with the hydrogen alone. So if you're going to look at this, what is the one that is happening in the anode? What is the reaction that is happening in the anode? Is it the hydrogen or the copper reaction? Anyone? What do you think happened here? Hello. Anyone? What happened in the anode? Is it the hydrogen or the copper? So, are you there? If we have this reaction, what happened in the anode? Which one is oxidized? Hello? Anyone? Okay, so it's the hydrogen. Now, how do we know? Okay, we're going to look at the given reaction. We can look at the table that we have here. Wherein we're talking about what? This one and this one. So if we're going to look at this, okay, so how's the hydrogen happening here? So you have H, if I'm not mistaken, H2, which is 1 atmosphere, producing 2H plus 2 electrons, right? Because lost electron. And the other one, you have copper 2 plus 2 electrons producing copper. So overall, if you're going to look at the cell notation here, or cell diagram, you have what? You have a platinum here. So that's another base. And then what do you have here? H plus, if I'm not mistaken. No, H2, because that's the one that you have. And then you can put there 1 atmosphere just to show you the condition. And then you have H plus, which you could put as 1 molar. And then on the other side, you have a copper 2 plus, 1 molar also, and copper. So that's the cell notation for this reaction. And if you're going to look at the reaction, the overall reaction here, you just combine the two, H2 plus copper 2 plus, producing 2H plus and copper. Now, based on this one, you have what? 0.34. Now, where will I put the 0 here? Is it the cathode or the anode? Where is the 0? Is it the cathode or the anode? Because we assign this always with a 0. Now the question is, where is the zero here? Is it the cathode or the anode? Anyone? Okay. So that is your what? Anode. Come on. Look where it is. If you're going to look at this, isn't it the same spelling as this one? So if that's the case, so that means potential of your cathode is 0.34. And that's how you end up with the value that you have here. Now, why did I say I prepare my students to use this formula? Because all you need to do is determine which is the anode and which is the cathode, and you don't need to change the sign of your reduction potential. Okay, this is unlike the previous discussion that we have. We have what? E oxidation plus E reduction. Okay, I think that's a little bit confusing based on experience. At least this one, all you need to do, you look at the table, and the table will tell you, okay, this is much lower, so this is the anode. This is much higher, so this is the cathode. And all you need to do is plug in the data. And you can get now the cell potential. Okay? So the thing that you need to remember here, as we discussed, the lower it is, the more likely it will oxidize. The higher reduction potential, the more likely it will be reduced. And if you're going to combine the highest and the lowest, it will give you what? A battery that gives you the highest potential. Are you familiar with lithium battery? This combination is the one that will give you the highest potential. Because if you're going to look at this, what do you have? So this is the cathode. So this is what? 2.87 minus the anode, which is, what do you get there in terms of the value? I cannot look at it now. What's the value that you have there for the lithium? Anyone? 3.05. So minus 3.05 minus minus 3.05. So that's the combination that will give you the highest value. And isn't it most of the battery that we have is made up of lithium? And haven't you wonder why lithium is the material that you have there? If you're going to combine the two, you're going to produce how many? Around 5.92 volts. Okay? So let's try to solve problems here using the table. So you have here, what is the standard EMF of an electrochemical cell made up of cadmium electrode in a 1 molar cadmium solution and a chromium electrode in a 1 molar chromium nitrate? So what do we need to do here? Okay. So what you need to do here is you look at the table and you're going to find what's the reduction potential of each of these material. So you can have oh my God, oops. Cadmium 2 plus and cadmium, and then this one with chromium. Now, most likely this is available. If not, the table should be given. Look at the reaction that you have there. This will give you around negative 40, and this will give you around 0.74 negative. So usually you have a reaction like this. Okay. So if you're going to look at the reaction there, so what is the anode and which is the cathode? What is the anode? Anyone? And what is the cathode?
Chromium is the anode.
Okay. Chromium is the anode. So what happened is you will have Cr producing Cr3 plus and 3 electrons. And the cathode will remain as this. So you have Cd2 plus 2 electrons producing chromium. And then you can put there that this is what? Negative 0.74. And this is negative 0.40. Why do I say I changed the value? I have 3 electrons here. I have only 2. So I multiply this by 2. I multiply this by 3. I end up getting 6 here and 2 of this. And then I have 3 here and 3 here. But I'm not going to change anything here. Okay. So the overall reaction that we have here, 2 chromium plus 3 cadmium 2 plus producing 2 chromium 3 plus 3. Oh, this is not chromium, this is cadmium. Plus 3 cadmium. Now what is the cell potential that I have? So all I need to do is I need to determine what is the cathode and subtract it with the anode. So the cathode that I have is the cadmium. So I have negative 0.40 minus negative 0.74. So what do I get?
0.34.
So you get this one. Now, when can you do this thing? When you have a galvanic cell. And when you have a galvanic cell, your cell potential will always be positive. You cannot do this approach if you're given a certain equation. So if you're given a certain equation, you follow based on the given equation, which was oxidized and which was reduced. What does it mean? If you're given, okay, a chemical equation, you don't need to follow the table. You follow which one is oxidized and which was reduced in the given equation. Now, if you're not given an equation, then you can use the table to determine which one is oxidized and which one is reduced. Are we clear on that? Okay. You only use the table if you're going to construct a galvanic cell. Okay. Because you need the table to determine the value of the reduction potential to determine which one is oxidized and which one is reduced. However, if a formula or if an equation is given, okay, telling you which one is oxidized and which one is reduced, you just use the table to get the reduction table or the what we call the reduction potential. And you might end up that the one that has the higher potential is not the one that is being reduced, and the one that has the lower potential is not being oxidized. Because you might be given there a reaction of an electrolytic cell. So I want you to remember that. Okay? When not to use the table. So if the reaction is given, you determine which one is oxidized and reduced in the given what we call reaction. If not, then you can use the table to determine which one is oxidized and which one is reduced. Okay? Now, how are we going to relate this chapter to the previous chapter that we have? So if we have a galvanic cell that will give us a positive result, so usually what we have there is a spontaneous reaction. And we can get another what we call formula here of your G. And this time with respect to the cell potential. So this was already given to you. This is the number of moles that is involved in the reaction. F is the Faraday constant, and this is the cell potential of the given reaction. And if you want it to be in the standard state, you're just going to put there this sign. So at standard state, you have what? 1 molar concentration, 1 atmosphere pressure, and 298 degrees Celsius. So in a previous meeting, the value of our F is around 96,485, but here they use 6,500. This value will be given to you. Okay. Now, what did we learn about delta G from our previous chapter? We can equate the delta G there in terms of K. So what does we have here? Okay, delta G is usually what? Negative if you have a spontaneous reaction, and when you have a spontaneous reaction, your K value is more than 1. So there's a lot of concept that is involved that can be used in your third exam. And you know what my worry is in the third exam? Okay, your practice exam comes first before the third exam. Okay, if you're doing well in your first and the second exam, I would suggest don't relax, because third exam is the most difficult exam among the 3. Okay, so it's a make or break for you in the third exam. And since you choose to take the makeup before the final exam, so that's it. Okay, so you hope that the other two exams and the quizzes that you have will be enough to push you to the grade that you want. So we can link this to the one that we have here right now. So delta G can be related to K and can be related to also the cell potential. And if we're going to look at how we combine these two reactions, okay? So if you're going to look at this is just like this one. And what happened? We just divide both sides by and F. Do you see that? So you cancel both what we call sign here, so you end up with this. That's the math there. Okay, and if you're going to put in the value, because these are all what? Standard values, so 8.314, which is the gas constant, and 298, and then the Faraday constant, we can have a shortcut like this. So what we're really looking at is the number of electrons that is involved in the reaction and the K. So I don't know by now if you still believe me that the magic letter in this course is the letter K. Okay? So I hope before the end of the semester, you will be able to place the O with the K. So what does this mean? Okay, this equation will be given to you. If you're going to relate this, what we call 3 things that we discussed: the cell potential, the Gibbs free energy, and the equilibrium constant. And if we're going to tabulate the relationship that they have, this is how they will end up. So this is a very, we could say, good source of questions in your multiple choice. Anyway, all the examples, that questions that you have are multiple choice. So if you have a negative delta G, that means you have a spontaneous reaction. You're going to have a K larger than one, and you have a cell potential that is always positive. It favors the formation of products. If you have a delta G that's equals to 0, that's a system in equilibrium, in your case equals to 1, and you have there a dead battery. If you have a positive delta G, you have a K there that is less than 1 because it favors the formation of the reactant, and your potential there is negative because that's non-spontaneous. That means you have to charge it. Okay? So all of this come the relationship that we just discussed in the previous slide. So let's apply this one here. So what is the equilibrium constant for the following reaction? Now, this is the thing. What did I tell you? You are given here now a reaction. And if you're going to look at this, okay, you have to determine which is the anode and which is the cathode, or which one is oxidized and which one is reduced. So which one is oxidized here between the two? Anyone? Is it silver or iron? Anyone? It's silver. Why? Look what you have here, silver, and then it becomes more positive. When do you become positive? If you lose electron. Does that make sense? And then this one is Fe2 plus 2 electrons. So I have to put here 2 electrons, producing Fe. Now, the next thing that we're going to do now is we have to find the E cell, wherein we have E cathode minus E anode. So let's try to look at the value of the silver and the iron from the table. So you have the silver that is here plus 0.80, and you have the iron. This is the right iron? No, that's not the right iron. The iron that you have is Fe2 plus. So that would be this one. So negative 44 and 0.80. Okay. So before I put it here, I'm just going to use the one that we have here. So we have one that is negative 0.44 and the other one 0.80. So this is what your Fe2 plus producing Fe, and this one is your silver producing silver. Now, which one is the anode and which one is the cathode? Anyone?
Fe is the cathode.
Huh?
Iron is the cathode. Right?
So the iron, so that would be what? 0.80?
Oh.
Is that how it is?
Oh no, it's negative 0.44 minus 0.80.
Oh, which one? The point four, negative 0.44? I think my mistake. And then the other one is
0 - 0.80.
now, as you're going to see here, you may ask the question, Professor, why is the anode has a higher reduction potential than the cathode? And I'll give it back to you. Why? Because you have no choice. You're given this reaction. Remember when to use the table to determine which one is oxidized and which one is reduced? That you're not given a reaction. Now you're given a reaction here and your hands are tied. Your hands are tied. Whatever I do, it's Fe2 plus that is reduced. And silver is the one that is oxidized. So most likely you don't have a galvanic battery or galvanic cell. What you have is an electrolytic cell. And how would you predict the equilibrium constant with this one? A negative cell potential will give you what? A K that is less than 1. So how are we going to solve it? So you have there the E cell equals to the 0.0257, right? Divided by N, ln of K. So you have now this value, which is a negative 1.24. If you're going to rearrange that, what you will have? You have ln K equals to E cell, right? Negative 1.24 divided by the whole thing here, 0.0257 divided by, what's N? What's the value of N there? Anyone? What could be the number that is equals to N here? 2. How will I know where I get this value? See this one? The number of electrons that is involved in a given reaction. So if you have that, what will happen? So I can eliminate the ln here by making it like E. So I have here this value, 1.24. Divided by 0.0257 divided by 2. What do you get? If you're going to do the calculation for the whole thing. E raised to the number that you have here. Negative 1.24 divided by 0.0257 divided by 2. So that's e to the negative 24. So I get that. What do you get? So I can, I think, simplify this one. I can put that on that. So E equals to 1.24 times 2 divided by 0.027. So 1.24 times 2 divided by 0.0257 E. I get around e raised to the negative 96.5. Which is around 1.23 times 10 to the negative 42. Okay? So, it has a negative value in terms of the cell potential. So that means the K is less than 1. And 1.23 times 10 to the negative 42 is really less than 1, because that means you have what? 41 0 before you have the 1. Question? Before we go on the effect of the concentration on the cell potential. So there's the one that's written there, how you get to that. Okay. So how do we look at the effect of the cell potential by the concentration? So we're going to start with this equation. So what's the difference between these two? Delta G is at any condition, while delta G not here is at standard condition. Okay, so if you're going to break down delta G and standard delta G, you will end up with this. So see the difference with this one? So if you're going to replace it here, okay, so you replace this one with this, so you end up with that one. And what do? We divide both sides by all what? Negative NF. You end up with this. And that is your Nernst equation. So what's the difference of the cell potential on this one and the cell potential on this? Anyone? Which is the one that we usually get from this reduction table? Is it the E or the standard E? Which is the one that you can obtain from the reduction potential when you what we call determine the cell potential of the cell by looking at the cathode value and the anode value reduction potential. So this is the one that you get from doing the operation in the table. And if you're going to simplify this one, we can get it like this. Now, which change here in terms of the concentration? How do we define Q? Anyone? Q is what? Products over reactants. So this is the one that will change the value that you have. Now, when is E equals to standard E? When Q is equals to what? What happened when Q is equals to 1? What is the value of L and Q? Huh? What is the value of Ln1 and what is the value of log1? Anyone? Hello? All you need to do is look at your calculator.
0.
Okay, so when Q is equals to 1, so this whole thing here will be equals to 0. So when you multiply it to this one, that will also become 0. So that's the time your E has the same value as your standard E. Okay? So that's the concept of this, what we call, by making the concentration different, you can have a concentration gradient. What is concentration gradient? When the concentration is different. And this concentration gradient is enough to give you energy or to reduce the energy. Okay? So let's try to work on this problem. So will the following reaction occur spontaneously at 25 degrees Celsius if the Fe2 plus concentration is 0.60 and the cadmium 2 plus concentration is 0.01? So what's the first thing that we're going to do here? We determine which is the one that is oxidized and which is the one that is reduced. So which is oxidized? Fe or Cd? Anyone? Huh?
CD.
Okay, so the one that is oxidized is Cd. Again, the Leora and the Geroa should be the one to help you. From 0, it becomes positive 2. So that means you lose 2 electrons. And the one that is reduced is Fe2 plus 2 electrons, giving you Fe. Now, the first thing for you to do is determine the standard cell potential. And if you're going to look at the reduction potential, so you have your Cd2 plus to Cd, and the other one is Fe2 plus to Fe, which we already know as what from the previous example is negative 0.44. Now this one is negative 0.40. So how will I arrange this thing here? So what is this, 40 or 44? Hmm? So it's 44 minus 40 or 40 minus 44? Remember, this is your cathode and this is your anode. So is this 40 and this is 44, or this is 44 and this is 40?
40 minus 44.
Is this like this? Or is it this one? Well, I think I have I should put a negative here. So which is your choice? The A or the B?
It's B.
Okay. To wake you up, type A or B as the choice. Type, which is your choice, A or B? Hmm? So let's see. What did you choose? Is it A or B? So some have A, some have B. So what could it be? The answer should be B. Did you get why it's B? It's 0.44 minus 0.40. Remember, what is the cathode here? The cathode is your Fe. So the one that is Fe is the 0.44. Okay? The oxidation, that's your anode. So you end up with what? What's the answer that you get here? 0.44 minus negative 0.44. So you have negative 0.04. Convinced? Now, that's not the end of the answer. Okay? That's just the beginning, because the one that we are asked is, what is the cell potential? Or will the reaction occur spontaneously? So all we need to do is determine the cell potential here. So what we have here so far is just this one. Okay, if you're going to look at this will be what? 0.0 minus 0.0257 divided by what is your N, and then you have an Ln that is equals to what? Based on this one, you have between the two, cadmium 2 plus, because that's the one in the product. And the one in the reactant is this one, Fe2 plus. And what is N? Anyone? What do you think is N equals to? N is equals to 2. Okay, so I'm going to place now the value here equals to 0.04 negative minus 0.0257. Oh, I hate this thing.
Why is n equal to 2?
Because that's the number of electrons that was exchanged here. If you're going to look at the charges that they have, from one is from 2 plus to 0, and the other one from 0 to plus 2. Got it?
Yeah, thank you.
And if I have an Ln here, so my cadmium is 0.1, 0.01, and my Fe is 0.60. So what's the value that I have here? And that will determine the answer. So that means if I'm going to get a positive value, the reaction will occur spontaneously. If I get a negative value, it will not happen spontaneously. If I get a 0, the system is at equilibrium. So what do I get? So you get around 0.0126, or to simplify it, around 0.013. So this is now spontaneous because you have a positive value. See, you just change the concentration, you can make a system that is non-spontaneous to be spontaneous. Question? Before we go now, what if we have a concentration cell and it's made up of the same material? Is it possible? Is it possible to have a battery that is made up of the same material, but they just have different concentration? The answer is what? Yes, it is possible. So I'm just going to what we call put this. So if you have what we call a battery that's made up of zinc, the only difference is one is made up of 0.1 molar and the other one is 1 molar, you still be able to get the battery. Okay? So how are you going to distinguish which one is oxidized, which one is reduced? So this is your anode and this is your cathode. So the anode has the lower concentration, the anode has the higher concentration. So what happened? If you're going to do a calculation on this one, this is the reaction. You cannot cancel them out because they have different concentration. But what do you think the value of your standard cell potential? Anyone? What do you think the value of your standard cell potential? What do you think the value of that? It's 0. Why do you think it's 0? Because you have zinc subtracting with zinc, and both of them has the same reduction potential. So everything will depend on this concentration. If the concentration of these are what we call the same, you don't have any battery. Okay? You have a 0, what we call potential system. But because of the one that you have here, so what's the value that you get? You end this. Okay? So you might say, is that possible? The answer is yes. And they're doing it. Okay? Constructing a battery that is made up of the same material but different concentration. Now, what I want you to do with the reviewer that you have, try to solve as many problems as you can in this what we call chapter. Okay? You have to use the concept that we have here as chemistry. I have my own reviewer. I have the chapter reviewer posted from the other section. So all you need to do is spend the time that you have to solve all the problems there. Okay? So what we have discussed so far are all galvanic cells. I have not discussed an electrolysis, although in some example we have an electrolytic cell, but we have not discussed about the so-called electrolytic cell per se. So just to give you the idea of the batteries that we have, so this is what, like a Planck cell or a dry cell. So maybe that's your Duracell. So the anode that you have there is your zinc. And then the cathode that you have there is ammonia reacting with manganese dioxide. That's the black powder that you have if you open a battery. You don't want to open it because it has what we call ammonia. And once it's broken, it can smell like the unclean restroom. Okay? So if you're going to look at the overall reaction, this is how it reacts. It's the zinc that is being oxidized. So you have a metal there. That's what we call zinc. And then you can also have a mercury battery that is not anymore used because you produce there a toxic pollutant, which is liquid mercury. And then you can also have, if you have your car, this is the chemistry in your car. Okay, so if you're going to look at this, okay, it's just lead that you have there reacting with lead oxide and then an acid, a sulfate producing lead sulfate and water. And once it becomes lead, all you need to do is charge it to restart again. And then this is the battery that most of us has used in our cell phone, the lithium battery. So this is how the reaction looks like. So this is the anode and this is the cathode. And then this is what they say, the future, the so-called fuel cell. Okay, so in the anode you have there what? You have an H2 reacting with hydroxide to produce water. And then in the cathode you have oxygen plus water producing hydroxide. I don't know if you read or watch some video that says a car can be run in water. Does that make sense? Can you develop a car that runs on water? My would say technical advice on that, if you can develop a device wherein you input the water and it produces energy, then fine. Because conventionally right now, what we know, water is usually what? You use energy to split the water to form what? Hydrogen and oxygen. But if you can have principle, just like what our body are doing, wherein we feed our food, and then what happened to the food? It's break down. When it breaks down, it produces energy to build up the small molecules like amino acids to protein. Then you can build a machine with that concept. But if you're going to build that, make sure you have to what we call higher security. Because if you're going to do that, overnight, some countries' economy will fall. You know what I mean? If you can build a machine that use what we call water as source of energy, you're going to kill a lot of countries' economy, especially those that import oil. Because if you said, oh, I was able to invent a vehicle that runs on car, overnight, the stocks of the oil will go down and it will bankrupt the economy. And overnight, you will be the most wanted person in the earth or the universe, and everyone will hunt for you. Okay? So that's what the thing, if ever water is possible. Okay? If you can invent a device where you feed water and it's going to produce energy enough to run the machine, then that's good. But it's unconventional today because water, for you to split water to hydrogen and oxygen, you need energy. Okay? So this is the convention that we have today. The spontaneous reaction is you have hydrogen reacting with oxygen to produce water. If you want to produce a machine that runs on water, that's the reverse reaction, which is really spontaneous, a non-spontaneous based on this logic here. Okay? So they also developed some bacteria power, wherein they have bacteria in the system. Okay? So you have there the acetate reacting with oxygen and acid to produce CO2 and H2O. So those are the things that we can look for the near future. Okay? Now, synonymous to this, what we call the contribution of electrochemistry to humanity, they also have one problem, and it has something to do with corrosion. Whether we like it or not, metals will deteriorate. So if you want to get rich, if you can provide a process where you can make the metal forever, then that's good. But if you're going to look at most of the metal, if not all of the metal, they are what? the structure deteriorate. Because why does corrosion happen? Anyone? Why does corrosion happen? And that is also the question, why are we living? It has something to do with oxygen. Okay? So oxygen will always cause or will be a good oxidizing agent. So oxygen, very good oxidizing agent. So it will cause the oxidation of metal. So your Fe can form first into Fe2 plus, further oxidation of Fe2 plus would result to Fe3 plus. If you're going to look at the redox reaction that is happening there, this is what happens in the anode. And this is what happened in the cathode. What's the classic example of oxidation? The famous landmark of Statue of Liberty. The Statue of Liberty is made up of what? Lady Liberty is made up of copper, and copper, as we know it as a metal, is color what? Brown. But look at the Statue of Liberty. In case you have not seen the Statue of Liberty yet, it is colored what? Green. So what you have there is already the oxidized form of copper. Okay? And it deteriorates more if you have acids that are present, like what we call acid rain. So it will deteriorate the corrosion. So what do we need to do? So the way that they do it, they use some sort of a sacrificial metal. So you can take advantage on the use of this so-called reduction table. So what do? You place another metal that will oxidize, okay, compared to the metal that you're protecting. And some of the metal, when they oxidize, they will form some protective layer to the metal that you're protecting, like what they're doing here, the cathodic protection of the iron storage tank. They put it an additional magnesium because magnesium will oxidize better than your what we call iron. And the good thing about this magnesium, the magnesium 2 plus that form, okay, they can what we call form some sort of a protective layer. In our country, we have this so-called term galvanized iron. So what they do is we put zinc mixed with the Fe. And if you're going to look at the reduction potential, the zinc is what? 0.76. The iron is 0.40. So which oxidize first? Okay. You oxidize the zinc first. And when they form some zinc oxide that serves as a protective layer to the iron metal, giving a longer lifetime to this what we call galvanized iron. That's the one that we use in our country as materials for a roof. Okay. So that's the what we call galvanic cell, or one that has spontaneous reaction. So the second part is electrolysis. So this is the one where you applied energy to make the reaction spontaneous. Okay. So this is the one that use energy to make the reaction spontaneous. The one before is a spontaneous reaction that produce energy. So here, an example that we have, NaCl. You apply energy to that, you can get the Cl2 gas and the liquid Na. Water, okay, is another example. So if you do this in your experiment, remember the Ki? What happened to the Ki, the experiment that you did? So you form an H2N, an I2. That's a Ki plus H plus, if you can remember, right? So one is, what do you call this? Some bubbles that form, and the other one has brown liquid. So what happened there is the battery convert I minus to I2, and it also convert H plus to A2. So those are the one that is present there. So those are, I think, the last experiment that some of you will perform next week. Okay? So for the water, that's why I told you it's hard to have a water running the machine, because the conventional is you need energy to break water down. So water can be used if you apply energy to produce oxygen and hydrogen. So that's the conventional thing that you have. If you're going to look at it, this is how it looks like. So this is similar to the thing that you observed in your last experiment. Okay, so you have the water, and then you put the source of energy, and then it will break down. Now, how are we going to calculate electrolytic problem or electrolysis problem in electrolysis? So these are the steps. So you're going to use the Faraday constant there. You have to know that the charge is just equals to the current times time. So what you're going to have, you're given the current, you get the time, and you can get the charge. And once you have the charge, usually you're going to divide it with the Faraday constant, because that's the number of charge per 1 mole of electron. So once you get the number of moles of the electrons there, what you're going to do, you're going to use the mole ratio in the reaction. And from that, you'll be able to get the substance that was reduced and oxidized, the number of moles of substance that is reduced and oxidized. And if you want to express it in liters and in mass, you just use the molar mass or the ideal gas equation. Okay? So what do we have? Let's solve one problem here. So how much calcium will be produced in an electrolytic cell of a molten calcium chloride if a current of 0.452 ampere is passed through the cell for 1.5 hours? So how are we going to solve this? We need to know the reaction. Okay, what do you think the reaction that we have here? So you have calcium chloride, so this will break down to what? Calcium 2 plus and chloride ion. So we could say here, okay, I have a 2 chloride producing chlorine and electron. And the other one, I have calcium 2 plus 2 electrons producing calcium. So which one is the anode and which one is the cathode here? Is this A or C? So which one is this? Is this A or C? So you have a negative there, becomes 0. So that means, okay, you become more positive. So this is the A, the anode. If that is the anode, then this is the cathode. How do I know it's the cathode? I have a 2 plus becoming 0. Okay? So if we're going to look at the reaction overall, it is calcium 2 plus 2 chloride producing calcium and chlorine. So how many electrons are involved? So I can say it's 2. So how we are going to do the calculation here? So if we follow this one, current and time to give you the charge. So I can look at the current as what? 0.452 ampere. Ampere is really coulomb per second. Now look at the time. The time that is given for me is 1.5 hours. So what do? I need to convert it to seconds. So how do I do it? So maybe 3,600 seconds per 1 hour, right? So we are now on the charge. We are now on this step. So what's the next thing that you're going to do? Divide by the Faraday constant. So what does it mean? I multiply it here with 1 over 96,500 coulomb per mole electron. So I'm already, if we follow the step here, we're already here. And what's the next thing that we're going to do? Use the mole ratio. So the mole ratio is what? For every 1 mole of calcium, because calcium is the one that's being asked, okay, there's 1 or 2 moles of electron. So what do we have here? We can now have here the moles of the calcium, right? And if you're going to do the operation here, this one is canceled, the R's is canceled, the second is canceled, the mole of E is canceled, so the one that's left is the mole of calcium, and that would be equals to what? Anyone? Because you can also convert that to the grams of the calcium. So the mole of calcium is equals to 0.126. And you're going to multiply it with, if I'm not mistaken, 40 grams per mole of calcium. So you will end up with 0.50 grams of calcium. So where do we utilize this electrolysis? I'm not sure if you have this experience, but I think this is one of the worst things that I experience. Dental filling. So they have to put it there. I think that's the consequence of me eating too much chocolate. So what you do is you're doing an electrolysis there. So they're putting this amalgam there that is made up of this what we call mercury. Okay. So that ends the chapter that we have. So these are the amount of the energy that you use for that. Okay. So what do you need to remember? I'm going to post chapter 18. No, I think I post already. No, chapter 17 answer key is posted. Chapter 18 answer key will be posted hopefully later tonight. And then the quiz on chapter 18 will be posted maybe by tomorrow, but it will end on what we call Tuesday. And then chapter 19, I think will be posted by Tuesday next week. Now, I put something here. Not this one. And I want you to answer this. Because just to let you know, the other section will not meet on April 15. And I might invite the lab sections that I have from that section to attend the April 15, because we're going to finish chapter 20 in one meeting. Because what I'm going to think about it, maybe we can meet on that, but you will be the one. I'm not going to record the meeting, so it's up to you what we're going to do during that day. which means if not not everyone will show up on April 15, April 13 will be our last day. Or by the end of the meeting, I will require you to show up your pace. Because I want to take a souvenir photo of my Gen Chem students, because that's the last time that we will have our formal class. And I think I can assure myself that none of you will repeat it with me, because no one will want to repeat it again with me. Not because you will pass the course, but it's not the sweet that, it's not sweet the second time around you take Gen Chem 2 with me. Okay? So, out of the 40 that responds, 27 say they want to meet on April 15. Okay? And I'm also thinking if I'm going to require you to do your OWL chapter 20. Most likely not. But please don't tell it to the other section. Because we will see. Okay? Secret safe with us. We will see what we'll do. Because I was surprised, those former students of mine who are not doing well in my class are doing well in the other class. But I know why. So I might incorporate that also at the last minute. Okay? So question. It's 1:35 already, so that means I have to change my clothes and go out and fetch my daughter.